Jnanam Paramam Dhyayam. Knowledge is supreme.
Okay, step 2, we have proved it is projective module. I will now prove it is principal. Extended ideal is principal. Remember, we wanted to prove that the P is principal, but now the step 2 says when I localize it at that T, the element we started with, that extended ring it is principal, and the third step will be the P itself is principal. Okay. So now let us look at the homological dimension. So we know that the global dimension of A is finite. Therefore, homological dimension of this P as a module, this is a supremum, so this is less equal to this, so this is also finite. But what does that mean? That means this P has a finite projective resolution. So that means P, we can write it as resolution like this, P0, Pn minus 1, Pn 0. These are finitely generated projective A modules. But they are over a local ring A. So finitely generated projectives are free. So therefore, actually I have a finite free resolution for P, and therefore when I tensor this, tensoring with B, but tensor B is what? Remember, B is S inverse of A, and S inverse is exact. So therefore after tensoring with B, it will remain exact, and these are the free modules, so they will continue to be free. So therefore I will, when I tensor, what do I get? I get 0 B tensor Pn over A, P naught B tensor P naught over A, and then I will get here Pb to 0. Pb is same as P tensor B, B tensor P. So, and these are now free modules, free B modules. So this ideal in B has a finite free resolution, and when each guy is a finite free module, and the lemma says in this case this ideal is principal. That was the lemma. So therefore by lemma Pb is a principal ideal. P is not projective, no, that we have not proved. See, the small p is not projective, and now step 1 we have proved. See, this is projective by step 1. And remember, therefore also I had to state the lemma for non-local rings, because this B may not be local. So that proves step 2. Now step 3, P is principal, and that is the end of the proof. So we know by step 2 Pb is principal. And we want to prove that it is principal. Okay, so this is what? This is S inverse of P, where S is a multiplicative set generated by the T. And this one is principal, so it will look like some generator x times b, but this x is element in b. X is, I can choose this x element in actually in P. So, x is in P, because this is extended ideal. I can choose a generator from the below. Anyway, if it is in B, then I can always multiply by a denominator. It is a unit, so ideal will not change. So, I can assume it is this. Now, this is in x is in P. Now, we look at this, all these powers of T, a T power n intersection. This has to be 0, because this intersection is contained in intersection m power n, and Krull's intersection theorem says this is 0. So, therefore, this is 0. That means, x cannot be contained in all these ideals. So, there will be n, so that x is in t power a t power n, but not in the next. So, choose n with x belonging to a t power n, but not the next one. And that means what? That means this x we can write it as somebody y times t power n with y in a. Then note, this y cannot be in at. If y is in at, then x will be in the next power. So, y is not in at. All right, and this x is in P, we know, that is how we have chosen x. If x is in P, then y t power n is in P, but t power n is not in P, therefore, y is in T, y is in P. So, y belongs to P. Once y belongs to P, look at the ideal generated by y in B, yb, this is contained in Pb, which is x times b, which is contained in y times b, because y divides x. This, so they will all be equal. So, in particular Pb equal to Yb. So, you see what did I do? Actually, I have chosen a good generator. To start with, x was a generator, but now this generator is not in the ideal generated by T. Okay. Now, I claim what? I claim, so claim is P is generated by Y in A. I know P is generated by Y in B, but I want to prove that now P is generated by Y in A. So, one inclusion is obvious, because P is in Y, Y is clearly contained in P. I want to prove the converse. So, let us take Z here, Z in P. I know this Z is here, therefore, it is a multiple of Y in B. So, that means this is Y times somebody in B, any element in B will look like A by T power n. A is in A and n is some natural number. And what does this equation means? So, this equation means, what does this equation means? That means you clear the denominator and you get y times A. So, this will mean T t power n z, which is y times a, which belongs to, we get this equation. What was t? What was t? T was a, remember what was t? And we have noted that it generates a prime ideal. That means it is a prime element, right? And so this side belongs to t. Therefore, product belongs to the prime ideal. Therefore, one of them belong to that ideal generated by t. But who can that be? Y cannot belong, right? Therefore, A will belong. So, this will imply A belongs to, actually keep doing it. So, A t power n. But this will mean this A by t power n actually belongs to A, because A has also power of t power n exactly. So, you cancel it. We are in a domain, so things are okay. So, therefore, what did I prove? This belongs to A, therefore, that Z actually belongs to YA. Because this is in A, so this Z belongs to capital A multiple of Y. So, therefore, and that is what we wanted to prove. We wanted to prove equality. We started Z in P and we wanted to prove it is in A. That is what it is. Okay. So, that proves its principle, and therefore, we have finished our proof that it is a UFD.